There have been several questions regarding the quiz and how to set up problems and what to do, and what I want to do here is give you guys a couple strategies, a couple key things that can help you when you're solving a problem. Okay? So I have an example problem here that's fairly complex, and we're going to go through it a step at a time, and I'm going to point out some key things for you to do when you're solving a problem. Okay? The first step is always going to be just read the problem straight through and figure out kind of what it's about. Okay? So a student was riding on a float moving at 15 meters per second during the homecoming parade. She was tossing a softball in the air and catching it at a height of 1.2 meters. Just after she threw the ball up at 10 meters per second, the driver of the float applied the brakes to avoid hitting a child diving for candy. If the float slowed down at 8 meters per second, how far in front of the softball player does the ball land? Ignore air resistance and assume the ball lands on the road. Alright, there's actually a whole bunch of information in there. Okay, so my strategy is always going to be to start with the picture. The picture does a couple things for us. It lets us sort out what numbers go with what objects, but it also lets us establish a reference frame so we know which way is positive, which way is negative, and we can hang all these numbers on these objects. Okay? So it says a student was riding on a float moving at 15 meters per second during a homecoming parade. So I need a road with a float. Okay, so here's my road, here's my float. Okay, and alright, there it is. And it says it was moving at 15 meters per second. So I'm going to go ahead and I'm going to put a little arrow here. 15 meters per second this way. Okay? I randomly picked that, but I'm going to say that that's positive. So up here I'm going to write this direction is positive. Okay? She was tossing a softball in the air and catching it at a height of 1.2 meters. Okay, that height, that 1.2 meters, so here's my person riding on the float. Okay, she's tossing a softball, which is different than the float, different than her. Okay, so she's tossing this softball. Whoops, I wanted that to be a different color. Okay, this softball, and it's getting an initial speed up of 10 meters per second. Right. Now, she's also riding on the float, so the ball is also moving this way at 15 meters per second, right? If they're together initially, then they have the same speed initially. Okay? Now, that means I get to add another direction over here. Okay? And I just said this way is 10 meters per second, and up I'm going to call positive. So now I have a positive y direction, but I also have a positive x direction. Okay? And we have to keep different directions separate when we solve the problems. I also know that this distance, the distance from the ground to the ball, where she's catching and releasing it, that's 1.2 meters. Okay? Let's see. Just after she throws the ball up, the brakes get applied, 8 meters per second. So whoa, all of a sudden this float's going to start slowing down. We have an acceleration. Okay? But it's after the ball is tossed. So we have an acceleration 8 meters per second. Okay? How far in front of the softball player does the ball land? Okay, so think about this and figure out why the ball lands in front of the softball player. Well, the reason she's able to catch it and release it, is because as she's moving this way, the ball is also moving this way, right? But if all of a sudden the brakes get applied after the ball gets tossed, the ball continues to move to the right, but the float slows down and stops. So here's what we have. I'm going to draw the ball. It's going up and over. So it's going like this. Okay? The float is also going to the right, but it's slowing down. So our job is to figure out how far in front of the person the ball lands. Okay, well that means we've got to keep track of the person, we've got to keep track of the ball, and we've got to keep track of the x and y motions. So I'm going to go ahead and I'm going to start a column for the float, the person, whatever. Okay, so here it is, the float. What do I know about it? Okay, well now that I have my picture, I know the float only ever moves in the x direction. The float's not moving up or down. So the initial velocity in x for the float is 15 meters per second. Okay? And it accelerates, but it's a negative acceleration because it's in the opposite direction of the motion, negative 8 meters per second. Okay? And I'm assuming that this thing comes to a stop, but I don't know for sure, so I'm not going to write that down. Okay? So that's what I know about the float. What do I know about the ball? Okay? Well, when it comes to the ball, we have to be careful because the ball is moving up and it's also moving forward. Okay? So since it's a different object, it's got its own column, and since it's moving in two directions, it needs to have two individual columns. Okay? So I'm going to split it up. What do I know about the ball in the x direction? Well, I know it's initially moving with the float at 15 meters per second. I know it gets tossed up in the air at 10 meters per second. So that's an initial velocity in y, 10 meters per second. I know that there is no acceleration on the ball because it gets tossed right after it's tossed, the brakes are applied. So the brakes on the float have no effect on the ball, so there is no acceleration in x. However, the ball is going to slow down and come back down because there is acceleration on y, that's gravity, negative 9.8 meters per second per second. It's negative because I chose up to be positive. I know an initial position in y. The ball starts at 1.2 meters, right? It says that she's catching and releasing the ball 1.2 meters up. It also says to assume the ball lands on the road, so I know a final position, y equals 0 meters. I just established the ball, or the height of the road, to be 0. Everything's measured from there, so it makes sense. Okay, so that's what I know in y. I know an initial position, I know an initial speed, I know an acceleration, and I know a final position. Okay? What I want to know is how far in front of the float the ball lands. Okay? So how can I go from all this information to actually getting this distance? Well, if I'm just looking at the ball, I need to know a change in position in x. Okay? But I don't have enough information to get a change in position of x because all I have is an initial velocity. If I want a position, I also need a time. Okay? So what establishes the time? Well, the y, the vertical motion, establishes the time because the problem ends when the ball hits the ground. So I'm going to look at this and I'm going to see, okay, how can I get time from that? In order to answer that question, I really need to know, well, what tools do I have available to me? What equations can I use to try to solve this problem? Okay? So if I just go ahead and write these equations out, right, kinematic equation 1, 2, and 3, I have final velocity equals initial velocity plus acceleration times time. Do I want that one? Well, that let me find time. Well, I don't know the final velocity, right? I know initial velocity, I know acceleration, but I don't know the final velocity or time. That's two unknowns, okay? And I can only have one unknown per equation. Second equation says final velocity. No, it does not. Second equation says change in position equals 1/2 at squared plus v naught t. Okay? Do I know this? Do I know the change in position? Well, I kind of do. I know where it starts, I know where it ends, so I can find its change in position. 1/2 at squared. Do I know acceleration? I do. Do I know time? I don't. I want to find it. Do I know initial velocity? I do. Okay, so this equation, I know everything but time, so it looks promising, so I'm going to put a little star next to it. But before I give up on this, let's look at the last equation. Final velocity squared equals initial velocity squared plus twice the acceleration times the change in position. Well, this doesn't have time in it at all, so I need time, so I don't want this equation. Plus, I don't know final velocity. So this one actually let me find the final velocity, and then I could go back to the first equation, but if I'm going to use two equations, I might as well just use this one. Okay? So let's go with the second equation and plug in all the numbers. Well, the second equation says change in position. Okay, so actually, you can rewrite that. It doesn't matter to me. You can say y equals 1/2 at squared plus v naught t plus y naught, right? Y minus y naught is change in y. So there it is. There's the equation as we originally learned it. So 0 equals 1/2 times negative 9.8 times t squared plus, this is the y direction, so I'm going to use the 10 times t plus 1.2 meters. Alright, so there's everything I know in y. I'm not dealing with x, so I haven't even looked over there. Okay? And from this, can I get time? Well, absolutely I can get time. It's a quadratic equation, but I can do it. Okay, so let me simplify it. Negative 4.9 t squared plus 10t plus 1.2. Now, I don't know if you guys have a calculator that can solve the quadratic or not. If you do, feel free to use it. You don't have to show me the quadratic equation. You can just let your calculator do the work. On my calculator, I've actually written a program that solves the quadratic for me. If you're interested in getting that program from me, come and get it from me. Okay? I can teach you how it works. Your calculator might also have that program on it as well. Okay? So program, execute quadratic. Okay? And what it does is it asks me for my three coefficients. So A is negative 4.9, B is 10, and C is 1.2. Right? Push enter and it gives me two answers because the quadratic has two roots. But a negative time doesn't make any sense, right? If we went back in time, the ball would have been at the ground. Well, it was never there. It started 1.2 meters off the ground, so we don't worry about negative time. But I do see I have this 2.15 seconds. Okay? So that means the ball lands 2.15 seconds after being tossed. Okay? So I do know the final, or I know the total time for the ball. So t equals 2.15 seconds. Okay? That's how long the ball is in the air, so I know how far it's gone just by taking that time I solved for in y and moving it over here into x. So t equals 2.15. Later I think I'm going to want this space, so I'm going to go ahead and draw a meter. Okay, so t equals 2.15 seconds. So what can I do with that? Well, I can figure out how far the ball's gone now. Okay? I have the same three equations, okay, and I'm looking for a change in position. I want the second equation again, right? The first equation lets me know a final velocity if I have an acceleration. Well, I don't have an acceleration, so it's irrelevant. The second equation says change in position is 1/2 at squared plus v naught t. Well, I know v naught, I know t, I can get my change in position. Third equation says final velocity squared equals initial velocity squared plus twice the acceleration times the change in position. Okay, well that equation looks promising because it's got a change in position, it's got an acceleration, it's got final and initial velocity, and I know the initial velocity, I know the acceleration is 0, so I actually know the final velocity is the same, but it doesn't do me any good because if I look at that, I'm going to put 15 squared equals 15 squared plus 0, so 225 equals 225, or 0 equals 0. That's true, but it doesn't help me solve the problem. I need to know this delta y. Okay, so it's, or delta x in this case. So delta x, second equation, equals 1/2 at squared plus v naught t. Okay? And happily, the acceleration is 0, so this term is gone. It drops out. And so I just am left with the change in position equals v naught, which is 15, times the time, which is 2.15. What are you doing? 2.15. And if I do that math real quick, 15 times 2.15, 32.25. Okay, so that means the ball is going to move a horizontal distance of 32.25 meters in the time it takes for it to reach the ground after being thrown in the air. Okay? So 32.25 meters is my horizontal change in position. But this is all for the ball. The ball is moving completely independently of the float because the ball got thrown up in the air and it's not attached to the float anymore. The float is moving along and it starts to accelerate backwards at 8 meters per second to come to a stop. Okay? If I want to know how far in front of the softball player the ball lands, what I need to know is how far did the float move. Okay? Now, can I say that this 2.15 seconds is the same amount of time that the float was moving? I can't. Okay? And the reason I can't is because the float is accelerating at a different rate and in a different direction than the ball was. It's a separate object. So I've got to do things with the float completely independently of the ball. Okay? So what do I know? I know an initial velocity, I know an acceleration, and I need to know how far the float goes. Okay? I need to know its change in position, its change in x. Well, okay, that's easy to get if I make one assumption. Okay? I need to assume it stops. That's why the brakes were applied. Okay, the float comes to a stop. So I do know the final velocity is 0. Okay? So let's figure out what I know. I know an initial velocity, I know a final velocity, I know an acceleration, and I would like to know how far the float goes. Okay? Well, I can use the third equation if I come over here and look. So I can say final velocity squared equals initial velocity squared plus 2a times the change in position. Okay? So final is 0 equals initial 15 squared plus 2 times negative 8 times delta x. Okay? And 15 squared is 225, so I have 0 equals 225 plus a negative 16 change in position. Okay? And if we go ahead and subtract over the 225, I get negative 225 equals negative 16 delta x. Divide both sides by negative 16, and we get 14.06. Change in x equals 14.06 meters. That means the float goes 14.06 meters before stopping. Now, there is technically one more thing I should check. I should check to make sure that the float stopped before the ball hit the ground. Okay? Because if it didn't, then the ball actually lands on the float and not on the ground, which changes everything. Okay? I mean, the problem set assumed it lands on the road. Did it? Well, let's just see. The ball was in the air for a little bit more than 2 seconds. Okay? How long does it take to slow down and stop if we accelerate at negative 8 meters per second from an initial velocity of 15 meters per second? So I'm just looking for time. I can use the first equation because I know final velocity is 0, initial velocity is 15, acceleration is negative 8. What's time? Well, if I take 15 divided by 8, I get just under 2. Okay? So 15 divided by 8 is 1.875. So I know it takes 1.875 seconds for the float to stop. So yes, the float does stop before the ball hits the ground, and so we're good to go. Okay. Now, do I actually know an answer to my question yet? The answer is no, I don't. Okay. I know the float moved 14.06 meters before stopping. I know the ball moved 32.25 meters forward before it hit the ground. The question was, how far in front of the softball player did the ball land? Well, the softball player was on the float, so the softball player also moved 14.06 meters. Okay? And so the difference between these is going to be the distance between the ball and the softball player. So 32.25 minus 14.06 equals 18.19 meters. Okay? So the softball lands about 18 meters in front of the softball player. So maybe the little kid doesn't get hit by the float, but they got pelted by a softball. I don't know. Okay? This is a long, complex problem. There's lots of things going on in it, but I don't want you to be overwhelmed by that. Okay? There's really, I guess, there's 3 major steps whenever you're solving a problem. The first one is to draw a picture. Okay? And a lot of students just won't do this, and I don't know why. Okay? Paper's cheap. Waste it. Okay? Draw the picture. What you get when you draw a picture is you get a coordinate system. Okay? And what I mean by that is you establish which way's up, which way's down, which way's positive, which way's negative. You get left and right. Okay? And you know which objects have which information. Okay? So it gives you a coordinate system, but it also organizes your data. Okay? And it's just a simple, easy way to do that. Okay, draw the picture. It helps. Step 2, list your knowns and unknowns. Okay, just because you put them in a picture doesn't mean that that's the only way you should display it. Okay, so I'm going to say list your variables. Okay, so that way you know what you know and you know what you need to know. Okay, but when you're listing your variables, it's important. You drew them on your picture where they go, so when you're listing them in a list, keep them separate. Okay, so if you have multiple objects, you have to keep those separate. Separate, separate. So separate multiple objects. Okay? And once you've separated objects, if they're moving in more than one direction, you have to separate the directions. Okay? So separate the objects, separate the directions. Usually it's just x from y. Okay? And then finally, once you've done all that, then you can go look at your equations. Okay? So list the kinematic equations. Because you don't know which equation to use until you've listed what you know, right? You can only have one unknown, so if you have two unknowns, you've either got to look for more information, or you're going to end up taking one equation and substituting it into another equation to actually figure out what's going on. Okay? If you can do this, okay, every problem is solvable, okay? But you have to organize your data. That's the key to solving any of these problems.